I am Neil Kataria, working as a postdoctoral fellow at the Korea University, South Korea. Today I am going to represent a talk on Arylene diamide-based supramolecular materials and their potential application in catalysis sensing and the room temperature phosphorescence. Arylene imide-based molecules exhibit the unique properties which allow us to apply them as a luminescence sensor, photocatalyst, triplet harvesting, and the organic photovoltaic devices. So we are going to discuss these three topics. In the first topic, we will discuss the Arylene amide-based dyed polymers, where this BT unit is chosen as a donor molecule, and which is joined to the acceptor molecules, that is naphthalenimide, naphthalene diamide, and the PDI molecule through the non-conjugated linker. So here we discuss their optical properties. See, we can see the absorption spectra of these polymers, which is the combination of the individual absorption of the donor and the acceptor molecule as they are joined to the non-conjugated linker. So here is the fluorescence spectra, and we get the fluorescence from the individual donor and individual acceptors, and then we check the lifetime studies by choosing the both wavelength for the donor and acceptor molecule, and we choose it that there is a minimal change in the lifetime of the donor molecule in the polymer as compared to the individual donor molecule, and the similarly with the acceptor molecule. But in contrast, in the case of NDI, the similar absorption behavior was observed. We got the two absorption band with respect to the donor and the acceptor molecule, and similar the fluorescence spectra. But in the fluorescence spectra is quite quenched with respect to the individual donor and the acceptor molecules. So we checked the lifetime studies, which we found at the both acceptor and the donor wavelength. We found that there is a decay in the lifetime of acceptor and the acceptor molecule when it is in the polymer form, and the donor molecule in the polymer as compared to the individual donor and receptor molecules, which shows that there is a strong PET phenomena is occurring in the BT NDI polymer as compared to the BT NI polymer. So now we discuss the BT PDI based polymer, where the absorption spectra of the donor and the receptor molecules overlap with each other, and there we saw that the fluorescence is completely quenched in the case of the BT PDI polymer. So we carried out the lifetime studies at the 520 nanometer wavelength and the 635, and this red shifted wavelength, that is 635. We found that the lifetime of the PDI in the polymer decay very fast and decreases as compared to the individual PDI molecule, and similarly the donor molecule also, the lifetime of decreases from the individual PD molecule when it is in the polymer form, which shows that there is the PET phenomena is taking place, and also the energy transfer from the PDI to the BT molecule in the polymer. So how to we carried out the CV studies, and to confirm this, the optical band gap of the PDI and the BT is the same, which shows that confirms that there is energy transfer is taking place. That's why the fluorescence is completely quenched in the polymer. So due to the phenomena of electron transfer and energy transfer, the fluorescence is completely quenched. And after that, we utilized this polymer for the sensing of the iron ions. So we found that there is an 8-fold increase in intensity, which shows that the binding of the iron inhibits the energy transfer and the PET phenomena, which we confirmed from the DFT studies and the cyclic voltammetric studies. We carried absorption spectra, which shows clearly the naked eye color change from the pink to the orange. And we found that there is a band at the 578 nanometer quenched, and the new band formed at the 493 and the 337 nanometer after the complexation with the iron. And we optimized the structure with the iron ion, and after the complexation, there is a change in the Homemade LUMO level of the of there's a change in the HOMO and LUMO level, and we found that the LUMO level of the PDI and the BT are the same. So there is no electron transfer in the case of the complex, which shows that there is the inhibition of the PET. And after that, what we did, we coat that we take some cotton fabric and coated it with this ensemble of the BT-PDI polymer and the iron ion, which is and the color of the cotton becomes pink. And then we embedded this cotton in the 6 ml fridge and passed the aqueous solution of the iron, 2 molar aqueous solution through this syringe, and the color of the cotton becomes pink, orange, as we found in the solution phase. And then we check the iron content in the filtrate, which is just the 12.43 micromolar, which shows that the iron is binding affinity of this polymer with the iron. And also we can extract the iron from the groundwater bodies. So this is a real-time application of the polymer. And then we check the morphology of the polymer after the binding with iron, which shows the porous assembly, which prompt us to utilize for the vapor phase sensing of the biological amines. And here we check this test strip with the spermine vapor, and it got completely quenched, which shows that the iron the spermine binds with the iron and it sequesters and it breaks the complex and the decomplexation of the polymer with the iron take place. And moreover, the pink color again appears. So it shows the off on sorry it shows the on off behavior. And also we check this real time application to check the spoilage of the food samples. As we know that the fish and mushroom is the one of the sample. When it gets spoiled, it starts liberating the spermine. So we take the fish sample and dissolve it in the solution of the complex of the BT-PDI with the iron, and keep it and store at the 0 degrees Celsius. And after 1 week, we found that this solution become pink and the fluorescence completely quenched. Similarly, with the mushroom sample happened. Thus, we can utilize this ensemble for to check the spoilage of the food samples. And as it shows the on-off behavior, which prompt us to develop the logic gates. Here is the logic gate. After that, we utilize this PDI-based PBI molecule as a photocatalyst by attaching it to the thiophene molecule at the day position, because this thiophene molecule has the property to undergo oxidative polymerization reaction in the presence of the gold ion. This derivative forms spherical aggregates, and when we add here is the solution of these aggregates, and when we add the gold ions, this solution becomes purple. And we check the morphology of this purple solution, and it shows some polymeric sheet which is and contains and embedded with the gold and embedded with the small particles that are the gold nanoparticles, which we confirm from the XRD studies and from the XPS, that which shows that the gold is present in the 0 state. And also we carried out the simultaneously cyclic voltammetric studies and the UV visible studies. We've checked that we check the reduction potential of the aggregates of these spherical aggregates, which comes out to be the minus 0.37 electron volt. And then we applied this same potential to the gold ions and check the UV visible spectra, which shows that forms the band at the 570 nanometer, which is due to the localized surface plasmonic band of the gold nanoparticles. And we also confirms the formation occurrence of the polymerization and this oxidative polymerization to the NMR studies and the mass spectroscopic studies. So you can go from the paper to get the further more knowledge. And here we draw the schematic presentation of the formation of this polymeric structure stabilize the gold nanoparticles. And Then we check this in situ generated catalyst as a photocatalyst in the Heck coupling reaction by using the aromatic halides with the vinyl pyridine in the presence of potassium carbonate as the base, and all these reactions went smoothly. Even when we change this leaving group with by the iodine as by bromo, chloro, and the triplet, the reaction went smoothly. To broaden the scope, we carried out the reaction with the aliphatic alkenes and larger substrates and the multifold hell coupling reactions. All the reaction went smoothly, and we also did the portable script by using this catalyst, by using this ensemble, and the portable strip also work as the same as in the solution phase. So and this portable strip shows the 7-time reusability. After that, we utilize this application of Arylene diimide in the triplet harvesting. One of the important challenge to observe the phosphorescence in organic molecules is to stabilize the triplet state by minimizing the vibrational and the oxygen mediating triplet harvesting. So we can so by choosing the Arylene diamond and by building their crystals and or embedded in the polymeric assemblies, we can stabilize the triplet states, and we can stabilize the triplet state. Moreover, the phosphorescence is the spin forbidden process. Thus, by incorporating the carbonyl group and the heavy atom, spin orbital coupling enhances, which promotes the intersystem crossing. So here is a pyrometallic devices, pyrometallic imide based molecules, which are appended with the which are substituted with the carbonyl group and the halogen group. Here is the bromo group and the iodo group, and then we check its optical properties, and it shows the band at the 450 nanometer upon excitation at the 380 nanometer, and its lifetime is 0.8 nanosecond, which shows that this band is due to the fluorescence. And here is a similar for the iodo substituted group, iodo substituted organic phosphor. And after that, we checked its fluorescence, its emission property at the 77 Kelvin. This band gets redshifted, and similarly happen with the iodo derivative. And the lifetime of this band is 7.7 millisecond, which shows that this is due to the phosphorescence. And to get the phosphorescence at the room temperature, we embedded this small molecule in the polymer at the 1% of this molecule in the PMMA polymer matrix, and we found that the similar emission behavior as we observed at the 77 Kelvin with the both iodo and the bromo derivative. So which shows that this phosphorescence due to the monomeric phase. And then we increase the weight percent of the small molecules in the polymer derivative in the polymer matrix, and here we from the fluorescence spectra, from this emission spectra, we found that this band redshifted to the redshifted and show the orange emission. And from the lifetime studies, we found that this is the phosphorescence band. This emission is due to phosphorescence with the lifetime of the 5.2 millisecond and the 0.32 millisecond. Here we see that the lifetime of this triplet state increases, that this triplet state is more stabilized in the aggregated phase, because with the increase in the weight percent in the polymer matrix, these organic phosphorus get aggregate, and triplet state is more stabilized, and that's why the lifetime increases. So to understand these interactions, we form the crystals of these derivatives, and the similar emission behavior was observed, but the lifetime increased to the 5.2 millisecond to the 11.4 millisecond in the bromo derivative, and similarly in the iodo derivative. And we found that the quantum yield of this phosphorescence is 26% with the bromo derivative, and the 48% in the iodo derivative. This is in the air. And when we did the similar studies in the vacuum under vacuum, and in the case of iodo, there is a drastically change in the phosphorescence quantum yield, that is 68.2%. So to study this interaction, we also carried out the X-ray X-ray crystallographic studies, and it shows the layer stacking of these molecules and the presence of the halogen pi interactions and the carbonyl halogen interactions, intermolecular interactions, which shows the role of the carbonyl and the heavy atom effect in increasing the phosphorescence in increasing the phosphorescence lifetime, stabilizing the triplet states, and the reduction in the vibrational dissipation in the small molecules. So here is a conclusion. So I want to thank International Symposium Organizing Committee for giving me the platform, Dr. Vanna Bhalla for mentoring me in academics and my research, Professor Manoj Kumar as a former head for providing me time to time guidance, Professor Dong Hun Choi as for supporting me as a present for conducting research after PhD, and Professor Subi George for giving me opportunity to work in his lab. And here is a small message for Professor Manoj Kumar, and I want to congratulate him on his retirement and for his tremendous academic journey and outstanding achievement. Thank you so much.